So can you see the board on Google Meet?
Sir,
Yes.
in the homework there was a question. It's like ED2.3 started 4.
Wait. I'll give the hint. In this class, I'll give the hint for all homework, okay? Then try again. That's why I told, again, I'll extend the, time. Again, you didn't attend morning class, I think. I'll extend the, timeline of that homework, okay? That homework. So because I should have discussed that one, I mean, that hints I should have discussed in the morning. That's why I put evening as a deadline, okay? I will extend that one. Look at here. We have taken this one, am I right? We had a origin here. Better to choose origin first, okay? So then, okay, we have taken some charges here. Q1 point charges. We have initially taken point charges, am I right? Q1, Q2, Q3, and this is Qi. Let me take this is ith charge, okay? Qi. This one is ith charge, which is whose position is Ri prime, okay? Ri prime vector from the origin, position vector of this charge, okay? And we have taken field point here, am I right? Again, from origin, we call that one as R, isn't it? R vector. So this is the point P where we found electric field, am I right? Electric field at this point from the origin, okay? So that electric field was depending on this separation vector, okay? So we have taken this one as italic R vector, isn't it? Then we have written that electric field as 1 by 4 pi epsilon naught, or summation over 1 by 4 pi epsilon naught, am I right? Qi divided by Ri square into Ri cap, isn't it? We have written like that, summation over I. Observe this one carefully. Again, you may be thinking how this electric field is a function of this R, okay? Look at here, once you fix the origin, okay? Again, these are the mathematical aspects, okay? Once you fix the origin, again, we are discussing electrostatics, okay? Where the source charges are at rest. So can it come a little bit here? Yes. The source charges are at rest. That's why this Ri prime, okay? Again, if italic R vector, I think that's equal to R vector minus Ri prime vector. Is that okay? This, again, if you move in space, okay? If you move in space, this Ri vector will not change. This R vector will change, isn't it? Are you getting my point? See carefully. If you move in space, if you want to find electric field at different point in space, okay? If you move here, okay? So in that italic R, again, this electric field depends on this italic R. In that italic R vector, okay, this Ri is not changing, okay? Once you fix the origin, so these are not moving. That's why this italic Ri prime, okay? So I have to write like this, isn't it? So this is not varying, okay? If you move in space, speak up. If you move the your whole coordinate system or origin, then only this italic Ri vector will change. We don't do that one usually. Is that okay? We fix the origin. So that's why. So because of that, but suppose let me try to rewrite this one if you are worried. Okay. So this is equal to summation over I 1 by 4 pi epsilon naught. Okay. Qi. Okay. Let me write Ri vector divided by Ri cube. Okay. Let me write like this. What is this Ri vector? R vector minus italic, R vector minus Ri prime vector. Can you see this prime? Is that okay? Divided by Ri cube. What is Ri cube? Mod of that one, am I right? Mod of that one cube, isn't it? Mod of R vector minus Ri prime vector, the whole cube. Can I write like this? Now what I am saying is, you are doing the summation, okay? While doing the summation, okay, or again after you have done the summation, okay, suppose if you move in space, this will change, this will not change. That's what I'm saying. If you move in space, position vector of this P will change. What you call position vectors of these, what you call, source charges will not change. Is that okay? So position vector of source charges will not change. So that's why, so this electric field is written as a function of this R vector, position vector of the point where you are finding the electric field. Is that clear? Speak out. Yes, one second. Can you hear me on YouTube? Yes, 1 second. Can you hear me on YouTube? Yeah. Tell me. Then this will change. We don't do that one, right? Once we fix the origin, we always fix the origin, isn't it? Why do you want to move the origin? If you move the origin, it will not change. We fix the origin. After fixing the origin only, we work out the situation. Am I right? We work out the theory. Yeah, speak out. Any question? Yeah. Yes.
This position vector of the source charge changes, but this field point, the position vector of field point is not changing here.
No. What I am saying is, if you move this point, then this position vector changes. Am I right?
Oh, okay.
That's what I am saying. That's why we have to write electric field as a function of this R vector. Okay? Is that okay? In that summation, we have to find electric field as a function of R vector. Because later, if you want to take divergence, gradient and all, those are point variable. Am I right? What is the variable you take, isn't it? We write this one as R vector means, so this is x comma y comma z, okay? So unprimed, am I right? We have taken like this. We have taken this one as xi prime, yi prime, zi prime, am I right? We have taken like this. This one as x comma y comma z. That's how we have taken, isn't it? So while taking, suppose if you want to take divergence of this vector field or grade or some curl of this vector field and all, okay? With respect to what you take the derivative, this x, y, z. Is that okay? Be careful in that. But with respect to what we do the summation, I. Is that okay? After summation, we have written that one as a function of R. But with respect to what we are doing the summation, charge and this vector, remember. Is that okay? Find the difference. Find the difference. After you do the summation, it will be a function of spatial, so coordinate of this point. You can say like this. Is that okay? That's a vector field, okay, which depends on the coordinate of the point. Is that okay? Yes. Now what I do is, I'll take the similar situation, but in this case, okay, I'll take continuous charge distribution. Okay, continuous charge distribution, not point charges. Earlier I have taken point charges, isn't it? Now I will take continuous charge distribution. Continuous means it's not point like charge. Charges are again so close together so that you can't differentiate them as a point. Is that okay? Continuous charge distribution, just like continuous mass distribution in some solid. Is that okay? Let me take continuous charge distribution here. Okay, whenever you have continuous, again, you can have three different type of continuous charge distribution. One is line charge distribution, charges which are over the, what you call, line, okay? Charges which can spread over the surface charge distribution. Charges which can spread, so in some volume, inside some volume charge distribution. Three different things will happen, okay? In any cases, we call that one as continuous charge distribution. Is that okay? In case of continuous charge distribution, look at here. So you have to divide these charges into small parts. You don't have other choice. Because these rules, everything exists for, this again, so this is for one charge, am I right? We defined Coulomb's law initially for one charge. Then we made, according to superposition principle, we made summation, isn't it? Like that. We have to first define the electric field. For one small charge, we call it as elemental charge. Can I call like this? Elemental charge. Is that okay? Let me rub out this one. Let me rub out this one. Is that okay? I call that one as elemental charge. Okay, so let me just symbolically write like this. Later I'll just elaborate in case of some specific situation, line charge, surface charge, or volume charge. Okay, I call that one as dq. Okay, there may be large number of charges. Okay, the total charge in this region, that may be capital, so this q. Okay, since charges are continuously distributed, so the total charge is q, I have divided that one into small q, infinitesimal charge, infinitesimal amount of charge. Can I take like this? dq, just like derivative idea. Okay, so now the location of this one, obviously this is a source charge, am I right? Location of this one, let me write r prime vector. Just r prime vector. You can't write I, because you can't count how many these infinitesimal charges are there. Infinitely many. If it is infinitely small, then in that whole region, okay, of continuous charge distribution, you have infinitely many of such charges, isn't it? That's why we don't count that one. Okay, we go for integral. Okay, we don't count that one. That's why I'm not writing Ri, but there I have written Ri prime vector. Am I right? So that I can make the summation. Okay, so I just write R prime vector here. So then let me draw. Why? Let me draw what you call, this is italic R vector. Is that okay? Now, due to this small amount of charge, let me define electric field here. Is that okay? Due to this small amount of charge, the electric field will be usually around R cap. Am I right? Let me write that electric field due to this small charge. Okay, electric field. So just you can write down electric field at R vector. Can I write like this? At R vector. That means I am pointing out this point in space with respect to origin. Okay, at R vector due to dq. Okay, due to dq at R prime vector. Am I right? dq is at R prime, isn't it? dq is at R prime. So I call that one as dE vector, because that is the electric field due to infinitesimal charge element. Is that okay? That's why let me write dE vector. Later I'm going to integrate. That dE vector is equal to 1 by 4 phi epsilon naught. Again, Coulomb's law only. Okay, dq divided by r square into r cap. Again, I just, where r vector is given like this. Is that okay? Now this is the electric field here due to the small elemental charge of this whole continuous charge distribution. Okay, then total electric field is a vector sum of this field, isn't it? But that vector sum is not summation, it is an integration here. Yeah, speak out. I mean, the lot of this kind of, again, this is infinitesimal charge element. There are infinitely many of them. That's why we don't go for summation, we go for integration. That's what I'm saying. What do you mean by superposition of charges? We don't have superposition of charges, superposition of fields actually. You have one dq, you have other dq, you have other dq. Each of those dqs are what you call forming electric field, isn't it? So they are so creating electric field at this point. You have to vectorially add that one. That is the superposition principle, isn't it? So writing electric field as E1 vector. Again, in case of point charge, so you have written that one as a summation. Am I right? E2 vector plus E3 vector plus and so on. Am I right? In case of point charges, you can count the number of the E1 is the electric field due to charge 1, electric field due to charge 2, like that, isn't it? That's what you have done. So, but here you can't do like that, because it is continuous charge distribution. What you have to do? You have to define electric field due to a charge element, elementary charge, infinitesimal charge. Then you have to go for integration of dE. So that's the summation. That was the summation. Am I right? Summation over EI vector. Can I write like this? There. But you have to go for integration of dE vector. Speak up. So now this is equal to, remember, integral. Again, you are doing integration, am I right? You should know with respect to what you are doing the integration. 4 phi epsilon naught, okay? 4 phi epsilon naught dq. I better to write again the as earlier. Again, let me write r square into r cap, okay? R square into r cap. Now remember, in this integral, okay? While doing the integration, what you have to do is you have to move this dq everywhere around this region, am I right? Speak out. Are you getting my point? Integration with respect to what? You found what you call electric field due to this one, am I right? Then you have to find electric field due to some other elementary charge, am I right? That means you are doing the integration over this region actually. Is that okay? Integration of dq by r square into r cap. I better write like this, 1 by 4 phi epsilon naught outside, okay? Integral of dq divided by r square into r cap. Is that okay? Now this integral of dq by r square r cap, let me write like this, dq, let me write again r vector by r cube, okay? So again that is going to be like this. R vector means r vector minus r prime vector, okay? Divided by mod of r vector minus r prime vector whole cube. Now integration with respect to what? Look at here, integration is not with respect to now this r. Earlier summation was with respect to ri prime. Now integration is with respect to this r prime vector. Are you getting a point? See the diagram properly. Integration is with respect to r prime vector. Earlier it was summation with respect to I was changing ri prime actually. Just try to compare that. Is that okay? And in this whole integration, look at here, this r cap vector is variable. If you take one elementary charge here, r cap vector is like this. Am I right? If you take other elementary charge here, isn't it? Suppose here corresponding what you call. So corresponding ri vector is different. Am I right? Again, this your italic r cap is different. This is a variable, okay? Observe that one properly. Is that okay? So shall I move on? That's how you are going to find total electric field. Again, that total electric field is a function of r. Because you are going to integrate out this r prime, okay? There are two things here, r and r prime. You are going to integrate out r prime, okay? You are going to substitute the limit and all. Then what variable remains? This r vector variable that will remain, am I right? That, now look at here. I have taken what you call a line, okay? My charges are distributed uniformly over a line, continuous charge distribution, okay? Charges are so close to each other, continuous charge distribution. So then what we do is we define line charge density. So the word density is used here, okay? That density need not be always per volume, okay? In case of one dimension, if there is any quantity per length, we call it as density. Is that okay? If you have two dimension, if there is any quantity per area, we call it as density. Is that okay? So usually we use density of mass like that, am I right? In case of what you call, so 3 dimension, mass per unit volume and all. But density is used as a most general word, okay? It need not be always 3 dimension. It need not be always per unit volume, okay? Density can be, again, in case of 1 dimension, okay? This line is a kind of 1 dimension, am I right? So it can be per length, okay? Again, now we are going to define line charge density here. Is that okay? There may be some total charge Q, okay? So there may be some total charge Q on, again, when you count the total amount of charge. But we define line charge density because these charges are closely spaced, okay? So we call it as lambda, okay? That lambda is equal to, suppose if you take a small portion of this one, okay? Suppose if you take a small portion of this one, let me call this one as DL, okay? DL, small portion of that one. Let me take that small portion contains a charge dq, infinitesimal amount of charge dq. let me take infinitesimal length of that whole line, okay, and that line infinitesimal length that contains charge dq, then this line charge density is defined as dq divided by dl. Is that okay? dq divided by dl. So this line charge density, it may be either constant or variable. Are you getting my point? You got two choice. This may be constant or this may be variable. That means, so you may have more charge density and at some region of the line, you may have less charge density in some other region. Okay, in the most general case, that line charge density, okay, so that depends on what you call the position here. Is that okay? And one more thing you need to observe, this line charge density is a point variable actually. Is that okay? Even though I have exaggerated here, okay, that's a point variable. Okay, we better to write like this. We better to choose the coordinate system again. Origin, isn't it? Usually, so it is dl, the charge is dq, okay, the charge in this this region is dq, okay, this position we are going to write it as r prime vector, am I right? R prime vector, somewhere here we are going to find the electric field, so that is r vector. Is that okay? And you can define italic r here. So just concentrate on here, okay, later we shall define electric field and all, okay, concentrate here. Now we define line charge density lambda, that's equal to dq by dl, okay, charge per unit length actually, but still we call it as line charge density, okay, line charge density. Now look at here, that line charge density, that may be different at different position of the line. That's what I told, am I right? In the most general case, it may be variable, okay? Speak out. Yeah, look at here. Do you have these things in a book, okay? Now look at here. So now, so that's why what we do is, again, what do you mean by different positions of this line? That means different r prime vector, isn't it? When you sweep here this dl, r prime vector is changing, isn't it? So that's why in the most general case, we write this lambda as a function of r prime vector. Is that okay? Lambda as a function of r prime vector. Okay? So because of that, we don't write dl, we write dl prime actually. Okay? It's a habit. Because this is somehow related to this coordinate, primed coordinate actually. This length. Is that okay? So this is how you define line charge density, okay? So in special cases, that line charge density may be uniform, okay? That charges may be uniformly distributed over the wire. So that charge per unit length may be same at all points, okay? In that case, what you can do here is, look at here, you can write line charge density. It will not be function of r prime, it will be a constant. Is that okay? Again, in that case, again, uniform line charge density. Uniform line charge density. Okay, so in that case, look at here, lambda of r prime. So again, it may be independent of r prime. Is that okay? It may be a constant. Is that okay? If that is a constant, look at here, you got two choices of writing that one. One is you can select a small region dl prime, okay, and you can find the charge in that small region dl prime, okay, small elementary length. Okay, you can write dq by dl prime. Okay, that's one idea. If charge density is uniform, you can write this one as total charge by total length of that wire also. Is that okay? Whenever you have uniform density of whatever the quantity you have, you can write like this actually. Suppose let me take what you call metal cube. Okay, let me take a metal cube. Okay. So I say this metal cube have uniform mass density, okay, dm by dv. This has a uniform mass density. Is that okay? Mass density is same everywhere, okay. Then I can take a small portion of this volume, okay, so of volume dv, okay. I can find its mass dm, okay. I can take the ratio dm by dv, isn't it? And I can find the density, isn't it? Or I can take the whole volume and whole mass, am I right? Whole mass, whole volume, I can divide, then also I'll get the density. Whenever density is uniform, this will happen actually. Is that okay? If you have elementary part of that one, if you have that volume, if you have that mass, if you take the ratio, you will get density. That density is same as if you take total mass and if you take the ratio with the total volume. Is that okay? Both will be same. When this can happen? This can happen only when the mass density is uniform. When masses are uniformly distributed. Can you feel this one? Speak out. So exactly in the same way, if charges are uniformly distributed, okay, you can choose a small portion of that one and you can take ratio of charge by that small portion length and you can define your charge density, or you can take total length. Suppose total length from here to here, okay, that is capital L, and total charge is Q. You can find total charge. So can I write total charge divided by total length? Is that okay? So that will happen when you have uniform line charge density. In that case, this will not be function of r prime. That means if you vary r prime, this lambda will not vary. Is that okay? This is the most general way of writing this. So in this case, you can't write total charge by total length. You can't write like this. If charge densities are non-uniform, you can't write like this. Okay? You have to take a portion because at different position that ratio is different. That is the meaning of the point that it is non-uniform. Are you getting my point? If charge density is non-uniform, at different portion, these ratios are different. So find this difference. In the most general case, you write like this. In the special case, you have uniform line charge density. You can write like this. Yeah. Now again, what we do? Again, we take this. This is a dq. Am I right? We find electric field due to this small portion of the charge, isn't it? Electric field due to this small portion of the charge. Is that okay? At this point, you can write this one as italic r, isn't it? So dE vector, that's equal to 1 by 4 phi epsilon naught, okay? dq divided by r square into r cap. Can I write like this? Speak up. Now look at here. Again, you are going to integrate later to find electric field, okay, at r vector, okay, at this position. You are going to integrate that one into 1 by 4 phi epsilon naught integral of dq divided by r square into r cap. Am I right? Now look at here. You can write this dq from this equation. dq is equal to lambda of r prime vector into dl prime in the most general case, okay? 1 by 4 phi epsilon naught, okay, integral of, what is the dq? Lambda of r prime vector into dl prime vector r square r cap, okay? If you see clearly that r vector, that's equal to r vector minus r prime vector, okay, that integral is over this r prime again. So that's why we write dl prime. Is that okay? If lambda is constant, you can take that lambda outside. If lambda is constant in case of uniform charge distribution, okay? Most of the case, questions are designed with a uniform charge distribution, okay? But they can design question with a variable charge density, isn't it? Speak out. This is in case of line charge distribution. Can I say like this? Line charge distribution. Is that okay? Let me take origin. Field point, okay? Now, suppose let me take the situation, okay, where my charges are distributed over the surface. That surface thickness is almost 0. Okay, surface means its thickness is almost 0. Is that okay? Let me take it like this. I have a surface and charges are distributed over the surface. Thickness of the surface is 0. Let me assume like that mathematically, okay? Now in that case, what we do is we are going to define surface charge density, okay? Suppose total charge may be Q, okay? Total charge over this entire surface, that may be Q, and its total area may be A, okay? Total area. So again, we define surface charge density, okay? That surface charge density is defined as sigma, okay? That's equal to, again, what we do is we choose a patch of area. So can you imagine? We choose a patch of area. Is that okay? So let me write its so position vector, that is again r prime vector. Is that okay? Suppose this patch have got area dA prime, okay, and it has got charge dq. Is that okay? That patch have got charge dq. Again its area is dA prime. Then that area divided by the charge. Sorry, charge divided by area. Charge divided by area, isn't it? The charge, the small elemental charge dq divided by its area dA prime, we call it in the surface charge density. Okay, surface charge density. Surface charge density. Is that okay? And in the most general case, this surface charge density is a function of r prime vector. Is that okay? In the most general case, it's a function of r prime vector. That means when you move a different region here, this ratio may be different. Is that okay? If the surface charge density is uniform surface charge density, uniform surface charge density, or uniform sigma, or okay, let me write uniform surface charge density. Okay, in that case, you can write this sigma, okay, as dq divided by dA. Okay, dA is area, okay, dA prime is area, or you can write a total charge divided by total area. Isn't it? Just like in case of uniform mass distribution, isn't it? You can choose a small portion and you can write you can take the ratio of charge divided by area of that small portion, or you can take the whole surface, you can take total charge, you can divide by total area. In that case, it's constant, it will be independent of r prime. That means even if you move r prime, sigma will not vary. Remember, these charge densities are point variable, okay? Densities are point variable. It's a function of a point, okay, r prime. Remember, you can define a charge density at a point, arbitrary point. Yes. Charge density depends, these are point variable, observe that fact. Is that okay? Now look at here, in that case again, this is a charge dq, okay, due to this dq, let me write this italic r vector, am I right? This is r cap vector, let me write electric field due to this small portion, 1 by 4 phi epsilon naught, am I right? dq divided by r square into r cap, isn't it? Now again, using this equation, you can write dq is equal to sigma of r prime vector into dA vector, so dA prime, not dA vector. dA is not vector here, okay? So now this is equal to, you can write 1 by 4 phi epsilon naught sigma of r prime vector dA prime r cap divided by r square. If you want to find total electric field, you can just integrate, am I right? 1 by 4 phi epsilon naught integral of sigma of r prime vector dA prime vector divided by r square into r cap. Remember, this r cap is variable. When you move this one, okay, this r cap varies. Can you imagine that one? Okay, that r cap is variable. And again, integration is with respect to this r prime vector actually, usually. Is that okay? We shall see that one. No, that infinitesimal difference, that is constant, isn't it? Just like I told dx, again in the earlier discussion, dx, the length is always same, isn't it? It's a derivative kind of thing, isn't it? We take that one same, remember. Is that okay? Sometimes dq may change, am I right? If you take different patch of same area, dq may be different, am I right? Then we say again that charge density depends on the, what you call, so that depends on the different position. Is that okay? We can say like that. Yes, you can write like this. We shall see how to do this kind of integral and all. Okay, this is in case of surface charge distribution. Shall I move on? Now what I do is, let me take a volume charge distribution. Is that okay? Charges are distributed throughout volume uniformly. Need not be uniform, but charges are distributed throughout the volume, okay, not on the surface. Okay, let me take this as a total charge Q, total volume V. Is that okay? Let me take like this. Is that okay? Then again, what we do, we take a small portion of this one, small volume of this one. We call it as volume element. Earlier, you can call it as area element, okay? So in the first case, in case of line charge, you can take line element, okay? This is volume element, okay? Use the word volume element. So let me write this as a volume D2, okay? D2, and it has a charge dq. And its location from the origin r prime vector. Is that okay? And this is italic r vector. Italic r vector. Is that okay? Now what we do, we define volume charge density. Am I right? We are going to write it as rho. In the most general case, it is a function of r prime. So that's equal to dq divided by d2. Let me write d2 prime. Okay? Speak out. Charge per unit volume. Like that. Okay? We define that one as volume charge density. Is that okay? And in the most general case, it may be function of r prime. Okay? If you take different, again, look at here. Once you say this d2 is the volume of the volume element, okay? All volume element, wherever you take, it has same volume. That was your confusion, isn't it? dA, that elementary thing, that is same, okay? Whatever you, so wherever you take, okay? So dq may be different, so that the ratio may be different, isn't it? So that again, in the most general case, it's a function of r prime. If you move at a different position, again, you may have different density, okay? In the most general case. Is that okay? Speak out. Now, in case of uniform volume charge density, okay, what you can write? You can write rho. Rho will not be function of r prime if it is uniform. Uniform is constant throughout the region of the volume, whatever the point you take, okay? That rho will be, you can write as dq divided by d2 prime, okay? Or you can write as total, so total charge, let me write this one as q total, okay? Total charge divided by total volume. Is that okay? Divided by total volume. In case of uniform volume charge distribution, uniform volume charge density, okay? So they may not say, in the question, they may not say uniform volume charge density, they may say charges are distributed uniformly. That means uniform charge density. Is that okay? Speak out. Again, the same thing. What you can write here, in place of dq, 1 by 4 phi epsilon naught, okay, in place of dq, so dq is equal to rho of r prime into d2 prime, isn't it? You can write rho of r prime into d2 prime r cap divided by r square, isn't it? You can just rewrite like this, integral of 1 by 4 phi epsilon are taken here, okay? Integral of rho of r prime d2 prime r cap divided by r square. Remember, so this is electric field at r, okay? Electric field at r, and integral over r prime. That's why we have written d2 prime. Is that okay? Speak out. Wait a second, we shall see example, okay? Example, we shall solve some problem. Then we shall see how r cap is variable, you can see here, am I right? If you take this, suppose if you have taken this volume element here, isn't it? Again, now look at here, r cap is like this. That's why throughout this integral, this r cap is variable, okay? Or you can write this r vector, italic r vector, as r vector minus r prime vector, okay? So this r prime is variable. That's why we put d2 prime over there, so that you should able to think like that. Integral is over primed coordinate. Primed coordinate r prime. This is unprimed coordinate. That's how we say. We say this is x prime, y prime, z prime. Okay. We say this is x, y, z. Is that okay? Speak out.
Sir, sir, but in equation there is d tau. Sir, how we will integrate it in terms of dr prime?
Which dr?
Sir, in equation electric.
Wait a second. We shall take example. Right now you may not feel that one. Okay. d2 prime. You will somehow write that one into r prime only. Okay. You'll see that one. Let me take some example. I may not go for volume charge distribution, but I can go for line charge and surface charge distribution. Okay.